Have you ever stopped to wonder why a massive explosion is over in a flash, but a simple chain might take your entire lifetime to rust? Well, it all comes down to speed. Not car speed, but the speed of chemistry itself. So today, let's get our hands on the controls and figure out the secrets to speeding up or slowing down pretty much any chemical reaction.
I mean, just look at this. On the one hand, you've got the crazy instant power of an explosion. Boom, it's done. On the other, the super slow, patient process of a chain turning to rust. They're both just chemical reactions, right? But they're on completely different clocks. So what's going on here? What's the dial that controls this incredible range? And that brings us right to the heart of it, reaction speed. You can think of this as the main dial on our chemical control panel. It is the key to understanding why some reactions are explosive and others, well, they take their sweet time. So what is it, officially? Well, reaction speed is just the rate at which your starting ingredients, we call those reactants, get turned into your final stuff, the products. It's all about how much stuff changes in a certain amount of time. Here's an even easier way to picture it. It's literally the speedometer for a chemical change. Is our reaction just cruising along in the slow lane, or is it hitting the gas and going full throttle? This speedometer tells us exactly that. Now, here's where it gets really interesting. We are not just passengers watching this happen. Oh no, we can actually get in the driver's seat. There are specific levers we can pull to either speed a reaction up or slow it way down. Okay, so we're going to focus on three of the biggest, most important levers we have at our disposal: concentration, temperature, and these really cool things called catalysts. Let's break them down one by one. First up, concentration. The best way to get this is to think about a party. If you've only got a few people in a giant room, they're not going to interact much, right? But what if you pack that same room full of people? Well, now they're constantly bumping into each other. It is the exact same thing with chemical particles. The more you cram into a space, the more they collide, and the faster the reaction kicks off. And this chart just lays it out perfectly. When the concentration is low, the reaction speed is kind of sluggish. But as you crank up that concentration, the reaction speed just shoots right up. It's a really direct, really powerful relationship. All right, let's grab our second lever, temperature. Turning up the heat is basically like giving every single particle a shot of espresso. They start moving way faster, zipping all over the place with a ton more energy. So not only do they collide more often, they slam into each other with a lot more force, which makes it much, much more likely that a reaction will actually happen. And that brings us to our third and final lever, catalysts. Now, these things are just fascinating. A catalyst is kind of like a chemical matchmaker. See, every reaction has this energy hill it has to climb before it can get going. A catalyst's job is to find a shortcut, a secret tunnel that goes right through that hill. It helps the reactants get together, speeds everything up, and then it hops out at the end, totally unchanged, ready to do it all over again. Okay, so we have our control levers. We know how to influence the speed. But science is all about being precise, right? We don't just want to say a reaction is fast. We want to know exactly how fast. And for that, we need a way to measure it. So the big question is, how do we actually put a number on it? How do we calculate the precise speed of a given reaction? Well, believe it or not, it all boils down to this really simple and elegant formula. V here stands for speed. Then you have delta C over delta T. Now that little triangle, that's just the Greek letter delta. And whenever you see it in science, it just means the change in something. So delta C is the change in concentration, and delta T is the change in time. That's it. Reaction speed is just how much the concentration changed divided by how long it took. Let's just run through a quick example so you can see it in action. Let's say we start a reaction, and at time 0, our concentration is 2.0 moles per liter. We let it run for 10 seconds, and the concentration drops to 1.5. Okay, so our change in time, delta T, is 10 seconds, and the change in concentration, delta C, is a drop of 0.5. So we just take that 0.5, divide it by our 10 seconds, and we get a speed of 0.05 moles per liter per second. See? Simple as that. Okay, this is all great theory, but what's the so what? Why should you actually care about controlling the speed of a chemical reaction if you're not in a lab coat? Well, as it turns out, this stuff matters everywhere. In industry, it means making life-saving medicines and the fertilizers that feed us way faster and cheaper. For the environment, it helps us figure out how to break down nasty pollutants more quickly. And it's happening inside you right now. Enzymes in your body are just biological catalysts, speeding up all the reactions that literally keep you alive. Heck, every time you cook, you're just using heat, our second lever, to speed up the reactions that make your food taste amazing. And if you need one number to really drive this home, get this. Over 90%, 90 of all commercially produced chemical products, basically the stuff that makes up our modern world, involve catalysts at some point. That's just how vital this is. So the main takeaway here is pretty clear. From these giant industrial factories all the way down to the tiny microscopic things happening inside our own cells, the ability to understand and control the speed of chemical reactions is, well, it's absolutely everything. So I'll leave you with one final thought to chew on. We've talked about the levers, the controls that we have over the chemical world. Now that you know how they work, what do you think is the single most important chemical reaction for all of human survival? It's a big question, something to think about.